I'm going to talk about some questions in quantitative topology, which is sort of an umbrella term, and I think people can understand that any way they want. But the way I see it is that we start off with some famous existence theorem, which in geometry, which is proved via algebraic methods. And we sort of try to uncover the geometry behind those algebraic methods. So the setting is a Riemannian geometry, which is the generalization of surfaces in R3. I mean, when we have a surface in R3, we inherit the geometry from R3 in the following way. Right, I mean, so we have...
You can't see the screen.
what am I supposed to do?
Jiggle the cable.
Maybe just a plugin? Yeah, that's already.
Okay, sorry, I'm going to remove this. Okay, so again. Technical difficulty. Okay. Okay, so we have R3, and there we have a surface, and we can look at a tangent space at a point. And first of all, there is an inherited inner product. Is because, say, given two vectors, we can just take an inner product from R3. Okay? So this inner product satisfies the following properties, as everybody knows: symmetric, bilinear, positive definite, and smoothly varying with respect to a point. And now that we have an inner product, we can define many things. We can define lengths of curves, angles, area. Well, I mean, we also have an inherited directional derivative because we can differentiate in R3. Given two vector fields on S, we can differentiate in R3. Of course, we're not going to necessarily get a vector field on S, but we can then project it. And this is the way we do it. And so, yeah, right, so this is just the formula that probably most of you have seen. This is what we do. Okay, so we can define curvature. So now we can also define curvature. And we can define some special curves that we call geodesics. So geodesics are generalizations of a line in the Euclidean space. And lines in Euclidean space, they have many properties. I mean, I'm not going to write them, but I'm just going to say it. They minimize distances between points, for example. They're certainly straight, right? Meaning that they satisfy a certain equation. If we are given 2 points, there is a unique line connecting them. If we're given 2 points in Euclidean space, there is a unique line of connecting them. They're infinite both directions. And so, I mean, there may be some other properties I did not talk about, but because we want geodesics to be generalization, we kind of should choose what do we want to generalize. And what we want to generalize is that the geodesics are going to be straightest curves that lie on a given surface. So this is informally speaking. Okay, so, right? So this is, so informally speaking, straightest, and formally speaking, this satisfies a certain differential equation. Okay, so we define first a geodesic at a point, and we say that curve is a geodesic if it is a geodesic at every point. Okay, so satisfying certain differential equations. Okay, so let's look at some examples. Now, the nice pictures that I will have, they're courtesy of my student Isabel Beach. She's from the University of Toronto. So we look at certain surfaces and we look at what geodesics on those surfaces are. And we can look at a round sphere, for example. This is a typical example to look at. And we see the geodesics on a round sphere. They are all of the big circles. Now it is easy to see that those are geodesics. One just needs to show that they satisfy the given equation that we just talked about. This is very simple computation. And it is also easy to see that there are no other geodesics because, and this is by uniqueness, because given a point in a tangent vector, we can find a plane that goes through the point and through that vector, intersects our sphere in a big circle. So there is no others. And so note that while lines, satisfy certain properties, we can kind of see, even looking at this here, I mean, there are more surfaces here, as you can see. And we can see that geodesics don't necessarily satisfy them, right? I mean, so first of all, if we, well, they're not infinite in all directions. Also, let's say we take 2 points, P and Q. Then how many, so we know that when we're given, 2 points in Euclidean space, there is just one line passing. But how many geodesics do we have passing through points P and Q?
You can speak about maximum than one.
So if we're talking about, okay, so you're talking about, if we're just talking about the minimal one, I think, distance minimizing one, then there is one. But, I mean, I'm sure you can see more than one geodesic if we don't specify distance minimizing, right? I mean, here's another one, right? I mean, we can go in this direction. But I will also claim that there is infinitely many, because geodesics are parameterized curves. We cannot just associate them with their images. And so we can go, for example, like this. And that's going to be a third one. And now you can see that indeed there is tons, right? But they are all, I mean, we say covered by periodic geodesic. So this is kind of a degenerate situation. Most of the times you will have those geodesics coming from different directions. But there always will be infinitely many, which we will discuss a little bit later. So you can also see that on a sphere, right? I mean, geodesic comes around, comes to itself, closes smoothly. You can kind of go around it again and again. And you can either call this thing, I don't know, I might have definition a little bit later. I'll talk about it in a little bit more specific way, but this is a periodic geodesic. If you look here, you can see that as you go around this geodesic curve, you come back at some time to a point, but it does not close smoothly. It comes with different direction. And when you have such a geodesic and it forms a singularity at the point, you call it a geodesic loop. So here's a question. This is the first question that we will discuss. Is there always at least one periodic geodesic on a closed Riemannian manifold? So closed Riemannian manifold, we generally call manifold that are compact no boundary. So this is a geometric term that one uses. So, I mean, we see there is one in a sphere. If your manifold is not closed, right? I mean, in Euclidean space, of course, there is not any. So that's clear. I mean, if you look at a cylinder, for example, I mean, there is a flat cylinder, right? I mean, there are geodesics of different type. I mean, there are ones. So on a sphere, all of them, on a round sphere, standard sphere, all of them are closed. If you have a cylinder, there are geodesics that look like lines. There are geodesics that just gonna wind around the cylinder. And there will be also closed geodesics. That look like this. Now, if we are somewhere on a hyperboloid. This is not a simply connected manifold, of course it's also not closed, and there will be no periodic geodesics or something like this. So this is something that's good to keep in mind. Now, so the question is, one of the questions one might want to ask, if you have a closed Riemannian manifold, should there be always one periodic geodesic? And in fact, if you answer this in affirmative, there is another question, famous question, other infinitely many, for example, one can ask. Now, one can ask, is there also, so when we looked at a sphere, given 2 points, we saw that there are infinitely many geodesics connecting those 2 points. One can ask, is it true in general? Okay? Now, if you make those 2 points, right, if Q equals to Q, then your geodesics become geodesic loops. And here you have an example of a geodesic loop, and you can ask a similar question. Now, so here is, so those questions about those curves are easier to answer when you are in a non-simply connected case, when you are not, your manifold is not simply connected. So, in particular, and this is a theorem of Cartan. So if you start off with a manifold, if you start off with a manifold that is, that is not simply connected, you can consider a free homotopy class. And Cartan's theorem tells us that there will be a geodesic corresponding to a non-trivial free homotopy class. So let me just summarize, right? I mean, so this is a theorem. So I'm just going to summarize a proof. Of course, you know, kind of the technical details are going to be a little bit hidden, even though, you know, the proof is kind of elementary and you can find it in the karma. So let me begin, and this is why I want to summarize it in a way that is a little bit different from karma, is because I want to use those techniques again. So let me, I mean, given a curve, there are many curve length shortening flows one can define. I like, kind of my preference is for discrete flows. I kind of can see what's happening. I find it a little bit cute, okay? So let me just discuss the Birkhoff curve shortening process, okay? So let's say we start off, and this is just a reference. So this is a reference you can use if you want to read it in more detail. Let's say you start off with a curve on a Riemannian manifold M, closed Riemannian manifold. Well, not necessarily closed, I mean, it's just defined, well, but if it's not closed, then, you know, we'll have some issues with convergence. So let's say this is a closed Riemannian manifold. Then you're going to have this process. It's going to depend, first of all, on the number of partitions. So n is going to be some number. And what number is this? Well, I mean, so we start off with a curve of certain lengths, and we want that the length of this curve, we call it gamma, divided by n is significantly less than the injectivity radius of M. Okay, so the injectivity radius, you know, this controls the size of the neighborhoods that are nice, that in many ways they are like Euclidean, and so we can, in particular, if the neighborhood is sufficiently small, if we're given 2 points on a curve, there will be a unique geodesic connecting them. So we subdivide this curve so that each of those neighborhoods is sufficiently nice, and we're going to replace this curve, by geodesic. So we're going to take those points, and we're going to connect this by a geodesic. segment. And we guarantee that it's unique. And we're going to do it for all those points, for all pairs of points. Then we're going to replace it by a geodesic. And so, well, at least we can see that the curve is not going to get longer by that, because we are shortening each part of the curve. Now, well, this is kind of discrete, right? I mean, we have to fill in between, but we can, right? I mean, we can fill in between. I'm going to use another color, it might get ugly, by doing this. Sort of by not replacing it right away, but replacing just a part of the curve and then connecting by geodesic. And so now we can see that we can do it continuously. Does that make sense? So there is a way to go between the original curve and the curves that we're getting. Now we're going to repeat this process. And we're going to repeat it by choosing middle points here. We're going to choose middle points in all those geodesics and do it again. Replace it by a geodesic. And so the question is, what's going to happen? Well, if we are on a plane, let's say, and we're doing this, right? We are going to converge to a point. On a manifold, you cannot always converge because it's not contractible curve, right? I'm going to converge to a point, right? And so Birkhoff proved, or maybe not Birkhoff, or somebody proved that you converge to a geodesic. Either it's a geodesic that is trivial, it's a point, or it is just a closed, non-trivial geodesic. So, so let me try if this is going to work. But Isabel has this little program that I'm going to run. Maybe it's going to be fun. So this is what's going to happen, something like this. If you do a, okay. Okay, so let me continue. So now the proof of Cartan's theorem, it becomes kind of easy because you take a, so let's say your arm is not simply connected. And then you take a non-contractible curve. And you apply the curve shortening, length shortening. It cannot converge to a point. It's not contractible. It will converge to a geodesic. So I'm going to call those things periodic geodesics. Klingenberg calls them closed geodesics. I just try to do that to distinguish them from geodesic loops, which are also closed curves, but they're not smooth. Okay, so here is a problem. I was told that I should suggest some problems, so here's the first problem. Show that for a not simply connected manifold, you can always find a periodic geodesic of length bounded by 2d, d is the diameter. Okay, so now that we sort of see that when you have a not simply connected manifold, there exists a periodic geodesic, the question is, what if it is simply connected? And it turns out that the answer is still yes. Even if your manifold is simply connected, there is the existence theorem, which is due to Lyusternik and Fet. I apologize, I've seen Lyusternik spelled in many different ways, so I might spell it differently as well, but I can never sort of pick the canonical way of spelling him. So if you want a reference, there is lectures on more serial than you, where it contains, in particular, the proof of the statement. So let me now discuss, so as we said, right, maybe we're going to be talking about existence theorems in Riemannian geometry, and their proofs and how to make them, should I say, less algebraic, something like that. Okay. So proof is by Morse theory on lambda m. Okay. Well, okay, so let me first define something. I'm going to define length and, I'm going to define length and energy functionals. So we're given a curve. Okay, maybe let me do something a little bit. Be a little bit more precise. So so I want to have something. I'll define it a little bit later. So I want to have something that resembles a calculus. Okay, right now. And to do that, if I have a curve, it doesn't matter whether it's closed or not. I can define something that is called a variation. Okay. And this is sort of introducing a curves. I don't want to write a lengthy definition, but we kind of introduce the curves that are in the neighborhood of our given curve. Okay, and what we want from those curves in the neighborhood of our given curve, that there is some regularity, so that then, like if they're not differentiable, there are a certain set of points in which they're not differentiable, etc. I mean, so in general, we are going to be dealing with piecewise differentiable curves, and that's because we would like to be able to define their lengths and define their energy. So, so this is going to be, so variation is going to be something like a function. And of our curve C. So this is a curve C. Okay, and so we can define then the length functional. And energy. And the energy and lengths are obviously related, but sometimes the preferred energy is easier to differentiate. So what we note right away is that critical points of length and energy functions are geodesics, and sort of depend on the type of space we're looking at, right? I mean, so we can look at the space, for example. So it's going to be a space of curves on n, piecewise differentiable curves on m. That connect P and Q. So we're going to take P and Q and M. And we're going to consider all piecewise differentiable curves that connect it. And you know, the critical point of the energy function is going to be geodesic connecting P and Q. Or instead we can look at the space, let's say, and this is what we are going to do, lambda M. So this is going to be all piecewise differentiable curves. All closed. On M. And then if you look at the critical point of the energy functional, it's going to be a periodic geodesic. Okay. So, so as we said, right? I mean, so the proof is going to be one more theory on the free loop space. This is called free loop space on M. I mean, so remember, I mean, you kind of remember this picture. No, it's just a torus, so this is not a free loop space on M. In fact, I don't know how to draw free loops, I may just sketch it. But a Morse theory gives us a way of studying the topology of a manifold, in particular the decomposition into cells, by studying critical points of the Morse function. Okay, so one kind of uses the symmetry that if you have this torus and it's empty and you start pouring water in the stores, right? I mean, if you view it as a vessel, and you see how the topology of this part of the torus that contains liquid changes. You see that it changes only when it goes through a critical point. And how does it change? It changes corresponding to the index of this critical point, where you glue a cell, as you pass through this critical point. I would like to do something similar here. This is my picture. This is my picture of the free loop space on M. I'm going to consider the energy functional. So what happens here, right? I mean, so it takes a curve, you compute its energy, you get some number, okay? Now I know that I can say something about the topology of this free loop space. So this is, this follows, right? I mean, so the two facts that I'm going to write follow from the homotopy exact sequences of a fiber ring, okay? And there are two equations, right? I mean, so first one is the Q's homotopy group of lambda m is pi q of m plus pi q of omega m. Now, omega m, I did not specify it, but I will. This is where is a space of based point loops. So I fix a point on M, and I look at all the piecewise differentiable loops that are based at that point. Okay, so I would like to have another paper, but I forgot how to add it. Okay, yeah, let me add. How do I add? No, I don't know how to add. What happened? I forgot how to add. Okay, I'm going to, since I forgot how to add, I want this to be gone. Okay, so I'm going to erase. I'm just going to make some space. Okay, so I have another one. I have another one of those equations, and that's pi q plus 1 of m is isomorphic to pi q omega pm. So from those two equations, we get that the q's homotopy of lambda m can be split as pi q of m plus, oops, I made a mistake. Something's wrong. Something like this. So this shows that there exists a Q such that pi q lambda m is not trivial, but pi q m is trivial. I mean, we are talking about simply connected manifolds now. For not simply connected manifolds, we already proven it. Okay, so I'm going to continue. So now returning to this guy. This is lambda m. Now here we have m. M sits as there is a natural way of identifying m with a subset of lambda m as a set of constant path. And remember, we are considering the energy function on lambda m. And we are going to, so we now know that for some q, there is a non-contractible sphere in lambda m. So I'm just going to look at this map. So there is a non-contractible sphere here. Look something like this. And I'm going to try and deform the sphere to m along the integral curves of the energy function. So I'm just trying to push it down to m. Now I know that if I push it down to m, now the sphere in m is contractible. I have selected q such that it's not contractible here, but it's contractible in m. So I should not be able to do that. And so what will be the thing that will prevent me from doing that? There will be a periodic geodesic. There's a critical point. I mean, we know that the topology is not going to change unless there is a critical point. So the critical point here is going to prevent me from doing this. So there is a periodic geodesic. Okay, so I'm going to now mention some other existence theorems. Okay, so another existence theorem, and hopefully we get to discuss many of the theorems that I will mention today, is a theorem of Serre, right? That given a pair of points on a closed Riemannian manifold, there exist infinitely many geodesics connecting them. In particular, if you may make them P and Q the same, this is going to be a theorem about the existence of infinitely many geodesic loops at a given point. Now, there is a classical theorem of Lyusternik and Zhou. Here I spelled him differently. Riemann also is spelled in many different ways, 1n, 2n, 7n. So, right, so on any Riemannian two spheres, there exist at least 3 simple periodic geodesics. So there is, I've mentioned that, there is this famous question by Klingenberg. So yes, I mean, now we know that on any closed Riemannian manifold, there are infinitely many periodic geodesics. Sorry, there is one periodic geodesic, but is there infinitely many? And while there are certain cases where we know there are infinitely many, in particular, we do know there are infinitely many on a two-dimensional manifold that was proven by Victor Bangert on surfaces, called surfaces. Right? We don't know this in general. In particular, if we take dimension 3, I think the current belief is that we don't know if there is at least 2. Always. Okay, so now here is another statement of a similar nature, and this deals with a free boundary problem. So free boundary problem is popular for minimal surfaces, but one can view geodesics as sort of dimension 1 minimal surface on hypersurfaces. However, surfaces, I don't know how to say it. They're not surfaces. Okay, submanifolds. Okay. However, one can see that if one wants the existence of minimal submanifolds, then there are certain regularity issues that one faces with in many cases, and so sometimes people prefer to see geodesic nets as the analogs of minimal submanifolds in dimension 1. But regardless of that, right, I mean, so one can ask, let's say we have a manifold. It's a little bit easier when it's closed, but no matter, I mean, we can just use complete. And let's say we have a submanifold. Will there always be a geodesic that meets the submanifold orthogonally? And this becomes, in particular, a particularly interesting problem when we have a manifold with a boundary, because then, we want a little bit more. We want not only that it means the submanifold orthogonally, we also want that the parts of this geodesic do not lie on the boundary. And that is, a little bit more difficult to achieve usually. So there is a bunch of results. So this is a result of Zhou that under certain conditions, so if n is not a deformation retroact of M, then we will find such a geodesic. This is another existence result, a little bit more new. I mean, just a little bit, here is a picture, right? I mean, this is what we're talking about. Also Isabel's picture. And there is a little bit of a history. So beginning with Lyusternik and Riemannian, who showed that if you have a disk in Euclidean space with a convex boundary, there should be at least n. So this is similar to this three geodesic theorem. At least it uses the same topological argument. What it becomes difficult to show that they actually, they lie in the disk. Then it was generalized by Boss, and then further generalized by Glock and Ziller. Now Hassan, Scott, and later Poe, but by different methods. I mean, so they showed that if you have a two-disk, then there should be at least two such geodesic chords. Okay, and so this is a recent paper by Giambo, Giannoni, and Piccioni that if you have one disk with concave boundaries, there exists at least n minus 1 geodesics. Now, and then, I'm not going to talk about minimal surfaces too much here. I probably will not have time, but I'm just going to mention, because there was like some serious development in terms of existence of infinitely many minimal solving Gauss conjecture. So, right, I mean, so starting with kind of old result of Algren, Pitts, Shine, and Simon, who showed that you can find a closed Riemannian, you can find a minimal hypersurface in a closed Riemannian manifold of dimension between 3 and 7, and then if and otherwise you might have some singularities. And the Gauss conjecture was that in fact you have infinitely many, and it's been kind of, I mean, I'm listening here, I'm just going to let you stare at this for a while, right? I mean, so there was like some serious progress by Marquez Neves and Liakumovich and Song, and eventually the theorem was proven by Song, by Antoine Song. So he proven the Gauss conjecture. In fact, there are infinitely many. Okay, so and then I said that the free boundary problem was also quite interesting to people who work in the geometric calculus of variation with minimal surfaces. And so there was proven an equivalent of this orthogonal chord conjecture where it was shown that there exists many free boundary minimal hypersurfaces. Okay, so this was sort of a long introduction, I guess. But now we are going to go to the main topic. Is that we can ask quantitative questions about all those objects that we say exist. Okay, so let me give you a few examples. And again, I'm planning to address many of those questions here. So here is the first question, right? I mean, so suppose you have a closed Riemannian manifold of volume denoted as it's written here. Can you always bound the length of a shortest periodic geodesic on M in terms of the nth root of volume? So this is a question that Gromov posed in Filling Riemannian Manifolds in 1983. I should say that in all generality, it's we don't know. Okay. Now, one can ask a similar question about the diameter. So, can you always bound the length of a Schur's periodic geodesic in terms of the diameter of a manifold? Now, note that if it's not simply connected, then it's bounded by 2 times the diameter. Okay, so maybe, it gives us some hope. I don't know, like, how generalizable this result. I mean, it's not really, but we will discuss it later, but maybe you can still bound it. Now, it is helpful to know the length, to estimate the length of a Schur's periodic geodesic when we know something about the curvature. And I will mention this again, but if you have, there are certain results for positive curvature, sectional curvature, and there are results for positive Ricci curvature, where you can bound the length of a Schur's periodic geodesic in terms of the lower bound on the Ricci curvature, for example. So, can you do it in terms of scalar curvature? This is a question of Gromov. Now, there are other things, right? I mean, there is a question, right? So I talked now about the theorems where the existence is known. But let's say we have a non-compact manifold. Well, I mean, we know that those things should not necessarily exist, but what if it has a finite volume? Okay, so this says the answer to this question is also still unknown. Also, again, if time permits, I will discuss the things that are known. And now, instead of stating more questions, is that we can state those questions about any minimal object you like. We can do it for segments, for loops, for orthogonal chords, for minimal surfaces. Similar questions can be asked. And so to be able to answer it, we should understand how those existence theorems work, really. Okay? So, so then, let me just try and see how can we possibly come up with those bounds. And in order to come up with those bounds, let me sort of briefly go back to the existence theorem. To the existence theorem of Lyusternik and Fet. Remember that to prove this theorem, we talked about lambda m. So points of this space are closed, piecewise differentiable, closed curves on M. Okay. And remember that we started with a non-contractible sphere. So we had this non-contractible sphere. So the points on this non-contractible sphere, those are again closed curves, right? And we try to push the sphere down to M. So what does it mean, push down to M? Push down to M means we try to simultaneously decrease the length of curves of the sphere. And we got the geodesic by the geodesic, right, was sitting below. What does it mean was sitting below? Its length was bounded by the length of curves in the sphere. So if we could actually come up with a sphere and say, here is an upper bound on the length for these curves, okay? Then that would give us an upper bound for the length of a periodic geodesic. And so, right, well, we call this, right? I mean, so when we actually construct this map, right, and it goes through non-contractible, it goes through this non-contractible sphere, and when we can say, well, here is the upper bound for the curves, we call this a sweepout, okay? So this is a sweepout. I mean, so the sweepout in general, there are many kinds of definitions. Every time I see it, there's a different definition. But in general, it is something that gives us a topologically non-trivial object. But in this particular case, it's not only that we want this topologically non-trivial object, but we also want that it's made out of objects of smaller lengths, okay? So if we can do it, if we always could have done that, then you know, we could have gotten the upper bound for the length of the shortest periodic geodesic, or if it was a different type of space, it would be an upper bound for something else. But the problem is that we usually cannot do it, okay? And so there are many examples, and the first example is this famous example of Franklin cuts, and I'm going to give you a reference. And this is, well, let's say you have a disk, right? I mean, I'm just going to be very general. I don't want to give you details because the details you're probably going to discuss during the discussion session. So, so let's say you have a disk, and this disk has, well, we know the length of the boundary of this disk. And you know the length of the boundary of this disk. And you know, the question is, can you really, and you know the diameter of this disk. And you want to produce some nice homotopy of the boundary that goes through short curves. So something, maybe, I don't know, that looks like this. I mean, is it always possible to do it? Okay, so this is kind of this was Gromov's question. So this is the first question that kind of comes to mind if you want to be able to do any type of a sweep out. So this is just going to be a problem. I don't know how to call it. Problem something. Problem in your discussion session. And then you can go further, right? I mean, so then you know you can, if you cannot do it, you can demonstrate that you cannot really sweep out a two-sphere by short curves always. Well, okay, so then one can say, how about sweeping out by cycles? Okay, so what are cycles, right? I mean, so suppose when you're sweeping out your sphere, suppose when you're sweeping out your sphere, you're allowing more than one curve in your, more than one connected component in your sweep out slide. Okay, so is it possible to do it when you allow your curves to bifurcate, so to speak? The answer is, well, still no. So then, you know, there was this question by Papasoglu. Okay, so now let's move one dimension higher. So if we move one dimension higher, so let's say you have a Riemannian 3 disk now, and you have both diameter and area, diameter, the area of the boundary, right? I mean, so I'll draw it. So you have diameter, you have area of the boundary, and you have volume. I mean, is it possible to contract the boundary in an effective way? And it was shown by Parker, Glenedy, and Zhou, and independently by Papasoglu and Svensson. There's still no. And then, you know, one can go, okay, but how about if you are sweeping out your Riemannian 3 disk, but not by surfaces of dimension 2, but by curves? Can you sweep it out by curves, by closed curves, so that you can control the length of these curves in an effective way? And the answer is still no. That was shown by Amaral Shawa and Henry Chen, who's here. Okay. So this, by the way, can be, so just to motivate this a little bit, so because, okay, so the answer is no, no, no to many of those questions. I mean, so first of all, the answer is going to be yes in some of the cases, okay? It depends what you want to control. And second of all, you can look at this last theorem as a first step in disproving Larry Goose's naive conjecture 4. So, well, it's a naive conjecture, so one should kind of believe that it's maybe not necessarily true. So, just as a curiosity. Okay, so now, I mean, so we kind of talked about when those, by the way, when should I stop?
Now.
Now. Okay.
No.
Now is a good time to stop. Okay, I'm going to continue tomorrow. Like at a schedule time,
Yeah,
I'm
we keep the
assuming.
schedule.
Okay.